All right, let's finish our conversation on risk and uncertainty. This particular little lecture is going to focus on quantitative risk. So how do we actually calculate it? What types of frameworks are available for us as environmental engineers? And then how does uncertainty impact our risk assessments? So just as a review, right, if it's maybe been a day or two since you've watched the other one, risk is a combination of both probability and impact, right? So we care about how likely an event is to occur, and normally we only have past data for this. And we also care about what types of impacts. So we can have environmental, exposure, human health, economic. Remember that triple bottom line with people, planet, and profit? Those are normally the types of impacts that we can have from a sustainability standpoint. And remember that sometimes different textbooks use different things for probability, so just be aware of how risk is calculated. So let's talk about some factors that influence risk. And not all factors influence all risk, but these definitely do have an impact on how we're thinking about risk. So people is kind of the big one. How people behave is not often rational or predictable. So as a result, many times how people behave is actually going to have an influence on risk. Things like voluntariness of the risk, so whether this is a risk that you voluntarily undertake, like skydiving, or if it's a risk that is involuntary, like having contamination all of a sudden happen in your water system, that's involuntary risk associated with you. Then there's also the factor of immediacy of the effect. So the more immediate the effect is, the more likely you're going to think it's risky. Your knowledge about the risk, so how much do you understand about the risk? So for example, I have a lot of knowledge about drinking water risk, but I don't have a lot of knowledge about air quality risk because that's not my specialty. There can also be the factor of control over risk. How much you can control the risk. So sometimes people try and control the risk of drinking water contamination by having Brita filters or fridge filters in their homes. There's also the factor of how effectively can we actually manage the risk, the severity of the consequence of the impact, and then whether or not the risk itself is chronic or acute. So chronic would mean it's going to happen over many, many years, and that's going to build into an effect maybe 20 years down the road, whereas acute risk is it's going to affect you today, and it's going to have a very big impact. So these are some different types of categories of risk. These are just some generic numbers that the textbook chapter that you can read, I think I had you read for last time, does. But we can have what we call familiar high occurrence risk. So unfortunately, this is things like vehicular risk. So driving a car, we knowingly, get in a car every day, high occurrence, it's very familiar. We can also have low probability events, so things like natural disasters, earthquakes. We can have events with low probability that have not occurred, but whose consequences deserve attention. So this is things like nuclear power plant failure, right? That is actually pretty low probability, but the consequence is really, really important. And then we have events that are hard to evaluate because they show up as increases in naturally occurring hazards, and this is things like environmental contamination. So this would be something like arsenic contamination. Arsenic occurs naturally, it's geogenic, but because of changes in the environment, changes in industry, things like that, arsenic can increase. And so the background levels can increase as a result. And so then it gets very, very hard to quantify this hazard. So I just want to take a look at the risk management process overall, and then we're going to go into some different frameworks for doing quantitative risk assessment. So at the heart of risk assessment, there are 3 steps: risk identification, risk analysis, and risk evaluation. So we need to know the analysis component, we need to know the identification component, and the evaluation component as engineers. So the bigger context is that we need to understand the problem that we have, and we need to mitigate the risk, and then we need to keep monitoring and reviewing and talking about risk in the system. But we do need to understand how to choose methods for risk. So if we're thinking about identification or analysis, there's many different frameworks we can choose as engineers to evaluate risk, and that's what we're going to talk about. So the other thing that I want to make sure that we talk about before we dive into those frameworks is that there's qualitative risk and quantitative risk. So there's qualitative, and sometimes we say semi-quantitative because it's very hard to qualify risk, right? Qualitative is going to focus on the relative risks of events, right? Like in relationship to something else. And the advantages of qualitative risk is that it's easy to prioritize, it's quick, it uses that risk matrix approach. You don't need a lot of data, you don't need people who are specialized, so it's easier to communicate and it's easier to use, right? The disadvantage is that it can lead to what we call fuzzy results or suboptimal allocation of resources. So because there is such a gray area between how we define low versus moderate risk, we can sometimes end up with these scenarios where we accidentally allocate resources towards something that doesn't need it, or we're not allocating enough resources to a hazard that really needs to be addressed. So it's good as a baseline to start. It's relatively easy to communicate, but it can sometimes lead to these issues of optimization. So quantitative risk management methods, there's lots of different, qualitative risk assessment methods, there we go. Many different things. Risk matrices, something called the MOTI method. There's a lot of international frameworks for this. So drinking water risk is done by the World Health Organization's water safety plans. Wastewater and sanitation risk is done by their sanitation safety plans. The transportation industry has the Department of Homeland Security. They have an air travel risk matrices. So a lot of industries use this format. Quantitative risk is going to be different. So quantitative risk is going to be an attempt to calculate values that can then be assessed against a specific criteria. So think of the probability density function, actually getting a numeric value, not using the risk matrix. And the advantage is that it's more rigorous. It's tested extensively in research and it focuses on very specific impacts. So we get the specificity that we want. The disadvantage is that it often requires an expert in a risk. So I do a lot of risk assessment. That's one of my specialties. And I'm always told to charge for my time as a risk consultant, right? And I don't charge expensive, exorbitant fees, but many risk experts do actually require that, it's a lot of time to complete, it's a lot of money, that kind of stuff. And the other big thing is that it has rigorous data requirements. You can't go into a quantitative risk assessment with very little data. You need a vast amount of data. And sometimes that's very difficult. It's hard to collect, time consuming to collect, all those things. So there's a lot of different quantitative risk assessment methods out there that we might see as environmental engineers. So if we're looking at microbial risk, we might see something called a QMRA. That's a quantitative microbial risk assessment. Drinking water risk can be assessed with a QMRA or exposure assessments. The EPA actually has a full exposure assessment protocol that you can look up if you're interested. A lot of environmental projects undergo an environmental impact assessment or a life cycle analysis. That could be a way of looking at risk. Life cycle analysis has a different focus. But environmental impact assessments or EIAs. The EPA has a ton of resources on risk. Transportation, the Department of Energy, the Department of Transportation, they all have resources on risk. Structural as a field, right? They have whole papers and interesting things on risk. So we're considering risk across civil and environmental engineering. And there's many places you can look, right, depending on your industry. When we've taught this class in the past, we've had people outside of environmental engineering take this class. So it's not just environmental engineers that need to know this. There's a lot of peer-reviewed papers. There's previously developed softwares, United States departments. They all have these resources. So if you start looking, there's actually quite a lot of frameworks available to you. So if we're looking back at this risk management process, right, it can get very, very complicated very fast. So I'm going to flip back to that slide for a second here. Oh, I can't in the recording. But the previous slide, right, shows the generic way of doing this. And what this slide is meant to illustrate is just how complicated this gets very quickly. So if you look at the risk evaluation component, you see all these fancy looking equations with sigmas and all this math, right, that you hopefully learned at some point. But it starts to get more and more complicated. So how we actually evaluate risk is why we end up having all these different frameworks for how we look at risk. So that component right there. So let's take a look at some different ways of evaluating risk. So one model that we could use is what's called a human health exposure assessment. And it starts with hazard identification, just like many, many risk assessments. And then it goes into what's called a dose response assessment. So we want to know what health effects people are going to see at certain levels of contamination. And then we also have a exposure assessment. So that looks a little bit more at different routes of transmission of a specific chemical. And we use both the dose response and the exposure assessment response to do a risk characterization. So the link at the very bottom of the slide actually takes you to the EPA's framework. That's where this comes from. And this is a way of looking specifically at human health and how different contaminants could have an impact on human health. So this framework could be one of those frameworks that we apply for risk evaluation. And this figure just shows the different types of health effects by pollutant and where we think about doses. So chemicals can be, absorbed through the skin. We can inhale them. We can ingest them. There's lots of different chemicals, and how we respond to each of those chemicals by each different exposure pathway has a different type of risk associated with what outcomes or impacts it's going to generate in the body. So the human health exposure model is really about understanding the pathway for a chemical to move through the human body and how it gets into the human body and what the impacts on the human body are going forward. In an exposure assessment, maybe you've seen these calculations before. You probably would have seen them in 321, CIVI 321 if you saw them. But they have calculations like chronic daily intake or average daily dose or carcinogenic risks. And there's a lot of fancy things that go into this, but basically you're looking at what's the concentration of what's coming into your body, how fast is it coming into your body with the intake rate, how much are you exposed to it on a daily basis, and then how many years are you exposed to it, what's the average lifetime, what's your body weight, what are all these different things. So a lot of different things go into this. We can talk about these calculations in depth if that's of interest to you. But just to show you that there are very, very specific frameworks that look at very, very specific things when it comes to human health exposure. So these are some of those calculations to take a look at. So we can have different exposure routes. So we can have the oral exposure route where we ingest something. And in that case, we have an ingestion rate. We can have the inhalation exposure route, and in that case, we have an inhalation rate, so how much air you're taking in every day. And we can also have dermal exposure, and that's going to be a little bit different because it's skin. So you're going to have a dose absorbed through the skin, and you're also going to have a surface area available for contact, so how much of your skin is in contact with the chemical. So you can see how this starts to change very, very specifically based on how things are moving in the system. And in human health exposure, we have lots of typical values, right? You don't have to make guesses on inhalation rates or intake rates. We know how much water people drink on a daily basis on average, right? It's not perfect for everybody, but we know, what's the area of human skin. We know, what an inhalation rate might be. And then there's going to be things that are specific to the contaminant itself that you have to go and look up. So at the very bottom of this slide, you'll see there's an exposure factors handbook that the EPA publishes, and you can go and look up all these values and look up different values for different chemicals. So really well documented type of assessment that you can do. We can also have what's called a QMRA. A QMRA is that qualitative microbial risk assessment. So this could be a different type of risk evaluation. And this is actually going to look a little bit differently at the source first. So this is mainly for water systems. It's going to look at the water source. It's going to do some water quality modeling. It's going to do the same type of dose response that we do for the hazard assessment, for the exposure assessment. And these three things make up the QMRA. But then we can also take those results and feed them into what's called a Monte Carlo simulation and do cost-benefit analysis and do some more decision support. So QMRA has a lot of the same factors, but it's really looking at water and what's in our water and what's specifically in our source waters. So there's another way of evaluating risk. We can also do cost-benefit analysis, which is a way of quantifying and weighing different benefits versus different costs. So what is a vulnerability? What's a hazard? What's the benefit economically? What's the cost economically? This is another way of evaluating impact. Because remember, risk is both impact and probability. So a lot of these analyses are looking at different types of impacts, right? So the cost-benefit analysis, the benefits are like the positive consequences, right? The possibility, you can possibly express it in terms of monetary units. It's really hard not to, in many cases, do the monetary units, but you can sometimes do that. And then the costs are the negative consequences. So they don't just have to be monetary, but many times they are. And then we can also have environmental impact assessment, right? So again, another way of looking at impact, and this one looks at environmental impacts. And so this is a process of looking at how likely it is that the environment may be impacted as a result of exposure to stressors, such as chemicals or invasive species or climate change, things like that. So they start with a very similar process. The whole process is the same, right? It's the generic steps, but they're just written slightly differently for each case. So we start with like screening and scoping. Like, is it even required? What's the scale of what's required? We look at an assessment of environmental risk, what data needs to be collected, what types of mitigation activities could occur, what decisions do we have to make, and then we keep monitoring. I think that's a good thing to point out for this one specifically. We don't just do the assessment and then mitigate everything and we're good. We keep monitoring the situation to make sure that we haven't missed anything that's really important. And the other thing I like about the environmental impact assessment is it has this component of stakeholder engagement. When we talked about social factors, we talked about how important it is to keep talking to people the entire way through a project. And I like that that's integrated into an EIA. The risk assessment component of an EIA is very similar to the human exposure assessment. We examine the stressors impacting the environment. So what are the adverse ecological effects? And this gets very, very complicated very quick. So there's some further readings on how to take a look at this if you're interested. Last thing that we want to talk about is uncertainty. And we want to ask this question, well, how certain are we about the risk to a system? And the answer to that is not simple. One of the first things that we have to think about is the risk assessment is only going to be as good as the data that informs the risk assessment. So then the question becomes, well, how much data do we need? How much data is going to eliminate a lot of these sources of uncertainty? And that's a really big question to answer, and it depends on the project. It's also going to depend on the scope of the assessments and the assumptions. So we talked about what is the system that you define in ENVE 210, right? When we do mass and energy balances, we draw a system boundary, right? And so if the scope of the assessment is too big, then there's going to be way too many factors influencing the system. And as a result, there's going to be huge sources of uncertainty. So the assumptions that we make about our boundary conditions are actually really, really critical to reduce uncertainty in a system. So that's something that we have to think about. And then generally when we do risk assessments, they need to be reviewed regularly. It's not a one and done management strategy. Sometimes they call them living documents because they're not supposed to be something that you put on a shelf. They're supposed to be something that you continuously iterate on. And that's because as more data becomes available, we can improve our estimations and our methods going forward. So the answer is no, we're maybe not super certain about a lot of our risk assessments, but we're as certain as we can be if we're addressing the things on the screen. So we're going to talk about just some basic principles of uncertainty analysis to kind of help ground what we talk about next. And the idea behind an uncertainty analysis is that we're trying to quantify the variability in an output due to the variability in the input. So if there's lots of factors influencing what's going into a system, it's going to induce a lot of potential factors that could affect why we're seeing the outputs we see. So variability in the inputs has a variation and the ability to cause variability in the outputs. And so we're trying to quantify that. We're not necessarily trying to reduce uncertainty. It's great if we can, but we want to be able to quantify where that uncertainty came from so that we can eliminate things that maybe don't help us. All right, so here's a couple scenarios. Scenario 1, we're given one data point, and based on that data point on the graph, looks like the risk is low, no big deal. So the decision would be, let's continue as normal. This is not a priority for us. Let's say in scenario 2, we're given a whole lot more data. We're given a distribution of data. And now the risk has a distribution as well. So the risk is going to be higher in certain areas and lower in other areas. And maybe the decision from this is to have a 5-year improvement plan. So what these two different scenarios are meant to show you is that the amount of data that we have and the amount of variability in our inputs directly has an impact on what decision we make, right? If we only have one data point with very low variability, we might think that's a low risk scenario. But if we have lots of variability coming in, it's going to have lots of variability coming out, and it's going to lead to different solutions and different decisions. So I'm going to skip over this one, but it's the same idea here. We've got uncertainty versus time and some different impacts, but I'm going to move on from this in the interest of keeping this video a little bit shorter for you. One thing that I do want to point out is that when we do uncertainty analysis, we're going to have lots of different inputs. And so what I showed you on the previous screen was one input. Now we've got, here's one input variable, here's a second input variable, there's going to be some kind of simulation in between, some kind of a risk analysis, and it's going to generate something on the other side that looks a little bit different. So basically what this is showing is that what's happening on the inputs, the distribution of what's coming in on the inputs has a direct impact on what comes on the outputs. So just to give you another example, let's take a look at this scenario. Let's say that we're given 12.4 crashes per year happen on London Bridge. 2 of those crashes have fatalities. Now we want to calculate, let's say the probability of a crash is 12.4 crashes per 365 days, so there's a 3.4% chance. At any given time, that's like a probability related to the probability of a crash happening, right? It's not the best way of looking at probability, but it's not a bad way to just get a number quick. Then the possibility of you crashing, right, is you could be, or death if you crash, right, is 2 out of 12.4 is about 16%. So that's what this little figure down here is showing, right? Here's crash, and then here's the probability of death from a crash, right? Very fatal. Risk is a very fatal or morbid topic to talk about sometimes because we always talk about fatalities. Scenario 2 is we're given the number of crashes per year on similar bridges to London Bridge, right? So instead of just having the 12.4, we now have 12.4 plus or minus a standard deviation of about 3.2, or just a deviation in samples. But then the number of fatalities is 2 plus or minus 6.1. So now we're starting to see that we have more data, there's more variability in the data, and then we want to look at what's the probability of, having death by a fatal crash on the London Bridge. And now we have to start intersecting things. Well, what's the probability of the crash based on 3 data sets and based on data that has a lot more variability, right? So this is kind of demonstrating that the more data that you have, the more you have to work with, but the more variables that start to influence your uncertainty as well. The other thing that I like to make sure that I always mention when we talk about risk and uncertainty is what's called a Monte Carlo simulation. And this is just a modeling technique that's used to predict the probability of a variety of outcomes when the potential for random variables is present. So what that means is if you have random variables for your inputs, what it does is it runs all the scenarios and all the variability in the inputs to generate all the potential outputs. So it's a common way for determining how input parameters impact the outputs. So what this figure shows is a starting point over here. Here's all our inputs, and look at all this noise. Here's all these potential pathways that you could take. And Monte Carlo simulations it's a computer simulation of multiple ways of doing this. We don't do this by hand anymore. So basically the idea with a Monte Carlo simulation is that we take lots of different inputs, we generalize them, and we get one big output in terms of a histogram or a distribution. So just as an example, right, let's say scenario 1, we have a probability of bridge failure and we have an impact, and we just got 1 point, and the risk is moderate, high. It's moderate, it's highly impactful, but it's highly unlikely. So the decision is maybe in 10 years, we're going to retest the bridge supports and determine if we need replacement. But in scenario 2, if we have lots of data about how often bridge failures occur in similar bridges and the average number of lives lost based on failures, we have a whole lot more information. And then risk might look different in the summer versus the winter versus overall. Maybe it's really icy in the winter. And what will happen is instead the decision will be something like implement a de-icing program for winter to reduce the probability of failure in winter months because we now have more data. So that's all this is trying to show you, is that there's a lot of variability in what's going on in our systems, and that sources of uncertainty are not necessarily bad, but it's something that we need to be aware of. That's going to close us out on risk and uncertainty. Bring your questions to class and we'll have a discussion about what big thoughts that you have after watching these pre-lectures.